Hello, everybody. I'm Paolo Abeni. I work for Red Hat in the networking services team. I do kernel networking, and I talk about OCP performances, as seen from the kernel stack. So this is the outline of what we are going to discuss today. We will see a little bit the OCP networking architecture and specifically OCP over Openstack networking architecture. We will see how GSO and GRO fit in the pictures about performances. And we will see what we can do to actually improve the throughput for our beloved pods in this scenario. But before diving into the actual subject, I must to do a little disclaimer. When I submitted this topic for DevConf, I didn't have any figures actually handy. So Scott Adams came to the rescue. And actually, there is a typo in there because Dilber says the wrong number. Do you know which is the correct one? Yeah, we will see later. So let's dive a little bit into OCP Openshift virtual network topology. There is our application running into a pod in a child network namespace. It's connected to the main network namespace with a couple of V8 virtual device. The virtual device in the main namespace is inserted in OVS Linux in OVS bridge. There is OVS switching in it that forwards the packet to a second OVS bridge. And here there is again OVS switching, and the packets are forwarded towards a Geneve UDP tunnel virtual device. This is built on top of the real NIC, and packets finally reach the wire. This is for OCP on bare metal, and it's actually quite simplified because several things are not showing up. But we are most interested in virtual OCP deployment and specifically OCP over OpenStack. And things became a little bit complicated because the whole diagram of the previous pictures is now the small box in the top left corner. And instead of a real NIC inside the guest Openshift node, now there is a virtio virtual network device that sends the packet to the host. And in the host, a vhost thread forwards the packet to a tap device. The tap device is inserted in an OVS bridge. And from now on, the forwarding is quite similar to the Openshift architecture. Most notably, there is a second Geneve UDP tunnel. So packets go through two levels of UDP encapsulation before finally reaching the wire, thanks to the hardware NIC in the bottom right corner. So one may wonder how a packet could really get out of there at any reasonable speed, given the overall complexity. But for OCP on bare metal, performances are not that bad, actually. If you try to measure throughput for a single flow with a good hardware NIC, you will get reasonable good high figure. Why? Because behind the scene, there is GRO and GSO taking place, meaning that whenever the application sends the data, the kernel stack will assemble GSO packets containing up to 64 kilobytes of application payload. That regardless of the actual MTU used by the egress device. The packet will go unmodified through all the network topology that we have just seen, for bare metal at least, until they will reach the egress NIC. In the worst case scenario, when reaching the egress NIC, they will be segmented by the kernel. That is, this giant GSO packet will be split in 43, 45 packets that will be MTU sized. In most cases, the kernel will not have to do such task because most NICs can do that for the kernel. The kernel will pass a giant GSO packet to the hardware NIC, and the NIC will do the work by itself. And so things will go fast. But it's not the end of the path, because there is also the receive side of the thing. On the receive side, while MTU size packet will reach the hardware NIC, and their GRO will take place. GRO is basically a technique that allows aggregating many wide size packets into a single GSO packet. Packets are aggregated basically when the headers of the to be aggregated packet match each other. And GRO will build this GSO packet that will be at most 64 kilobyte wide. And the whole packet will traverse the same network topology in the opposite direction until it will reach the pod and the receive buffer application. And that means that for 64 kilobyte, we will pay the forwarding overhead only once instead of the 43 times that we should have paid with 1500 byte size MTU packet. And that leads to overall good performances. But unfortunately, we are not discussing about bare metal. We are interested in OCP over Openstack. In OCP over Openstack, we have seen that the egress device for OCP is the virtio network device. And virtio does not support TSO for UDP encapsulated packet. The virtio device is not able to do the segmentation for work for the kernel. The kernel has to do it by itself. And this is because the virtio specification that mandates what a virtio device could or could not do does not describe at all GSO for encapsulated packet support. So does not sound that bad because we just have a little segmentation at the end of the OCP stack. The problem is that that segmented packet with MTU size will have to traverse the whole Openstack topology and go through the tap device, go through VOS, tap, OVS, Geneve, etc. So the virtio, the forwarding overhead experience will be very relevant, much more than the cost of actually producing the data or copying them from user space to kernel. Additionally, there is another problem because on the receive side, GRO can take place because Linux has no support for double encapsulated packet offload, nor any other operating system has support for this kind of packet. So GRO is not able to aggregate the double encapsulated packet that OCP over Openstack build. And this means that on the receive side, small MTU size packet have to traverse the whole Openstack topology and the whole OCP topology, experiencing a lot of overhead. So there is an additional smaller problem, let's say, with double encapsulation. So this is the layout of the double encapsulated packet generated by OCP or Openstack when reaching the wire. On top, there are the header created by the pod and the application. This is the encapsulation created by Openshift when reaching the Openshift Geneva tunnel. And this is the encapsulation added by Openstack when reaching the Openstack Geneva tunnel. When reaching the Openstack Geneva tunnel, if by some magic we will be able to generate a GSO packet that will arrive there unsegmented, still Linux has no support for double encapsulation. So before adding the second encapsulation, the kernel will have to segment the packet. What we can possibly do? So one thing is very obvious. We have said that the virtio network device has no support for TSO over UDP tunnel because the virtio specification did not specify it. So the obvious step is introduce the support in the specification and implement it in the device. And actually, the specification has been recently updated, and there is a proof of concept implementation of that specification, and the upstreaming into the Linux kernel of that implementation is a work in progress. The implementation itself is actually quite simple because to be able to segment an encapsulated packet, what the kernel needs is to know the location of all the relevant headers inside the packet itself. So virtio needs just to add the metadata for the additional header introduced by encapsulation to the virtio net header that is exchanged between the host and the guest. And this is not enough to allow our GSO packet to reach from the guest pod inside Openshift to the hardware NIC egress device inside Openstack, because as we have just seen, there will be segmentation in the Openstack Geneva tunnel. How we can avoid that problem? There is a very nice kind of load available in the Linux kernel, which is GSO partial. GSO partial allows devices that have no support for UDP tunneled GSO packet to actually segment them in hardware with very little help from the kernel. The problem is that the hardware device are able to handle a single set of headers, and with UDP tunneled device, we have two sets of headers. So what the kernel does to help them is, this is our GSO encapsulated packet with a single level of encapsulation, and all the lengths inside that headers are roughly 64 kilobytes. Prior to sending the packet to devices supporting GSO partial, the kernel just updates the out headers with values fitting the wire size. So it set IP length to 1500, UDP length accordingly, and fixes the checksum and handle it to the driver. The driver just needs to update this header here and consider everything below like a giant MAC header. It's constant data that can just copy. So it updates a header here and split the packets. It can do most of the work. How can we use this thing? The funny part, the relevant part, is that here the driver touches only a single set of header. This is an encapsulated packet with two sets of header, but for driver perspective, it's just a set of header. So we reduced the number of header, the number of set of header by 1. And we can do the same thing for double encapsulated packet. So the outer Geneve UDP tunnel can expose this GSO partial feature, and the kernel will prepare the already encapsulated GSO packet, as we have just seen. Note that now the length are lower, because if the final egress device has still 1500 bytes MTU, and we need to fit some more stuff in the packet, we need to reserve space for that stuff. So the kernel will do partial segmentation, the packet will remain a GSO packet, and Geneve can add, the second Geneve tunnel can add the second set of encapsulation headers, creating this quite strange looking GSO packet. It's quite strange. Who knows why this packet is strange? Who can see it? Okay. Yes, exactly. The, let's say, nested encapsulated header have this inconsistent length with respect to the actual packet length, which is 64 kilobyte. But that is less a problem that you may guess, or actually is really the trick that helps the kernel be able to actually handle offload. That helps the kernel and the NIC factory handle offload for this kind of packet, because this whole section here is considered constant. So the only headers that will be touched during segmentation are this one and this one. That means a single level of encapsulation, logically speaking. This means that this can be handled by simple single level encapsulation segmentation. And actually, the binary layout of the packet on the wire will be correct. So far, so good. We are able to now to transmit a GSO packet from the OCP pod up to the wire, almost unmodified. But we still need to handle the other direction, the receive path. On the receive path, we still have the problem of double encapsulation. We need to teach GRO how to handle double encapsulation. And doing it in a generic way is substantially impossible, but we can use some help from the Geneve protocol. The Geneve protocol allows adding user-defined arbitrary option that contains arbitrary data. So the sender can add one of these options that basically describe the layout of the above headers, where the inner headers are located, where the nested headers are located, and send the packet on the wire. The packet are received on the other end. GRO takes place. It parses the outermost header the normal way and try to aggregate them. And so far, so good, because the first few headers just plain EP, UDP, things that GRO is able to understand. When it reaches the Geneve header, the Geneve GRO callback is called that interprets that special option, if it found it, obviously, and find the location of the inner header inside the packet. It tries to match everything in between here. If this section is constant, and it will be constant if the packet comes from a segmentation on the other end. If that section is constant, it's just send the packet again to GRO for the innermost header parsing. And the core GRO is able to parse that header, because for the core, at that point, this is just a single level of encapsulation with some unusual large constant section in between. And the core GRO will aggregate the packet, and will generate the 64 kilobyte GSO1, and that we can travel unmodified up to the, I anticipated the contents of most slide, sorry. It will go unmodified up to the destination pod. And this will be the layout of the GRO aggregated packet. It's similar to the layout of the GSO partial packet we have seen on the other end. And specifically, we'll have the same weird thing in the middle. And again, that weird thing in the middle is the one that actually allows this packet to be segmented using a single level of segmentation and actually yield correct results on the wire. Yeah, I'm still speaking about the next slide every time. So with all these things together, now a GSO packet can travel from the, let's say, source pod inside Openshift towards the Openshift virtual networking, towards the Openstack virtual networking, to the other end, towards GRO, Openstack networking, Openshift networking, to the final pod, and we will pay the forwarding overhead only once for 64 kilobyte of data instead of 44 times that overhead. And this gives good performance improved. And we are also finally able to do the benchmarking that I was not able to do before submitting the proposal for this presentation. And these are the results I collected. So the baseline results were collected using Openshift on a full-blown Openshift deployment on top of a not so full-blown Openstack deployment, because the actual deployment of such a thing is way too complex for my capacity. So I actually sort of emulated Openstack below Openshift, maintaining the key point of having this additional encapsulation, but with a considerably simpler setup. The kernel used was the vanilla kernel for 9.6, and I had two use cases. One is intranode traffic between pods laying on the same Openstack node, possibly different Openshift node, but belonging to the same Openstack node. And the other one is for traffic between pods living in different Openstack nodes, different Openshift node inside different Openstack node. The green column is the same test done with a patched kernel that included the virtio support for GSO over UDP tunnel, all the funny things about double encapsulation support. The actual figures were 375% better for the internode case, and 470% better for the intranode case, which is actually not far off from the initial estimate. So Scott Adams would be happy. And that is basically all I have. The work is available at the moment as a proof of concept code. As say, the virtio implementation for GSO over UDP tunnel is currently being upstreamed. That upstream process will require still quite a bit of time because of funny dependency that raise it in the process. And since we have some time, perhaps I could elaborate more on this topic later. And afterwards, the double encapsulation support for GRO and GSO as upstreaming is still to start, and I foresee some problem for that because there are some corner cases that still need to be ironed out. So I think that the main takeaway you could take from this presentation is that GRO and GSO are basically the holy grail for networking performances. Any kind of networking performances can be resolved with some level of aggregation. And I think that is actually inspiring if we consider that nowadays many persons seem to think that problem should be solved by dividing people. Okay, that's it. I actually have a bonus slide because you have probably noticed that there were no nice diagrams in the slides, and there were no nice diagrams in the slide because I draw them myself and I can draw well. I actually asked help from AI because you need to ask help from AI, and this is what obtained. This should be a TCP packet with double encapsulation, as you can notice. It's quite obvious. Actually, this is the best result I got for it. I went to several attempts trying to use different wording, and this, if you look it for far away enough, it looks really like OCP network topology. You just doesn't have to read the text, and probably don't know well, but if I say this is OCP network topology, it will be quite credible, I think, no? Okay, that's it.
Okay, and if you have questions, please raise your hand. I'll bring you the mic.
Thanks. Thanks for the talk. What would be your estimate of impact of small traffic with very small UDP packets, say DNS traffic, which has packet heavy but small payloads? Yes. Any improvements in that regard on the horizon, or no?
Okay. So the question is about small packets, how we could handle that, and which is the impact of small packets on performances. Small packets are indeed extremely bad for performances. Luckily, we talked about TCP. TCP takes care of it for us in most cases. If an application writes even a few bytes at the time, TCP will wait a little bit to send the data to actually create the packet, and we accumulate more data until we accumulate enough data to actually create a good size GSO packet. For when we are talking about small packets, we are mostly talking about UDP. Nobody uses UDP, so there is no problem. No, actually, somebody uses UDP, but more often than not, is use it for the wrong reason and with wrong goal. For example, many persons say, I use UDP for performances, and that is plainly wrong. Some people say, I use UDP for latency. That could be correct, but considering that you are going to see that huge overhead a lot of time, in the end, even latency is to be worse on UDP than on TCP. But still, if you are really hardcore and really hardcore UDP packet transmitter, there are some things you can do because GRO can be applied. GRO and GSO can also be applied to UDP. It's supported by the kernel. It's not enabled by default. It can be enabled on a per socket basis, both on the transmit side and on the receive side. Openshift, since sometimes has actually support to enable GRO for UDP traffic at the forwarding level. So even if the application sends small packet, the networking behind the sign will try to aggregate them and create larger GSO packet, reducing the forwarding overhead. That kind of thing has a downside, because for TCP it's very easy to know when we need to stop aggregation, because the protocol itself tells it when to stop. There is a push flag that says you should stop here the aggregation. For UDP, there is not such a thing, so there is a timer somewhere to actually stop the aggregation, and the timer actually introduces some latency.
Should have kept the mic. Just to be clear, I understand that you are saying that TCP is much better for throughput and so on, and I understand from network stack developer that TCP is much easier to deal with than lots of small packets. But my point is that with a quick protocol on horizon, we will see much wider use for UDP than just NTP and DNS, basically. So that's why I'm asking. Thank you for explanation.
Specifically for quick protocol, the thing I said about GSO applies verbatim. That is, the application doing quick transfer can can tell the kernel to create a GSO packet for the data that the application pushes to the UDP socket, and the kernel will create a UDP GSO packet. And at least the transmit side of what we have just discussed will apply to that kind of packets.
So as an alternative to, or maybe a supplement to this double encapsulation support, have you looked at whether applying the other kind of listification bulk processing, so we don't aggregate the actual HTTPs, but we just bulk them through the listification thing? Would that work as an alternative, or?
So the question is about using a slightly different kind of aggregation to aggregate the packet. The kernel, beyond the usual GSO thing, it's able to do a fragment-based aggregation that actually it's extremely bugged, and especially for tunnel, it yields to very bad results. It was very easy to crash a kernel using.
No, I didn't mean the fracs thing. This API where you collect a bunch of packets and process them at each stage in bulk, but don't aggregate them.
So listification, you're talking about listification. Listification is another feature of the Linux kernel that allow processing a small burst of packets at every stage in list, instead of passing every single packet between one layer and the other. It has the main benefit that reduces considerably the amount of extraction cache misses, because the same code is executed multiple times in a closed window of time. The point is that the gain that listification gives compared to GRO are much smaller in terms of performances, because, for example, each packet header of the wide size packet needs to be visited at every stage. Listification is still in use by default under the hood.
Running out of time.
Oh, sorry. Meaning that the kernel uses listification whenever it can, from the NIC device up to the routing in the receiver path, but not in the transmit.
All right, we're out of time. Thanks a lot for the lively discussion. I'm sure it can continue in the hallway track. Thanks, Paolo, for your talk.